So, welcome to everybody. My name is Renata Hodovan and came from the University of Szeged. For the sake of variety, the next presentation will also about fuzz testing, but instead of investigating a nice test generation technique, we will approach from framework side with special focus on web browsers. It's years now that I'm working with web browsers one way or the other. First, I started as a developer of WebKit and Google Chrome. But soon enough, I realized that I enjoy more finding the bugs than creating them. So I started to play with fuzzing, and I created a framework that I called Fuzzinator, which was able to run one browser with one test generator. But as time passed and test generators and targets spanned, I needed more and more complex and dynamic framework to handle all of the components. And today, after a couple of hundred bug reports, several security reports, I believe that Fuzzinator is complex and generic enough to say that it's outgrew being just a browser framework, but it's a general fuzzer framework instead, with special focus on web browsers. And I hope that others can make use of it too. So I decided to release it. And this is why I'm here today, because it's open source from today, and you can access it from GitHub. But much talk and less said. Let's see what you can expect in the next presentation. First, I will give you some indisputable reasons why you will want to start with fuzzing just after you leave this room. After this, we will discuss what are the mandatory components of a fuzzer framework and what are those features that can ease your life even further. After this, I will introduce Fuzzinator. We will see how it works, how can you use it, how can you customize it. And at the end, I will show an example test generator that can cooperate with Fuzzinator and that you can use out of the box to fuzz any web browser. So let's start it. A few words about the motivation. So why do you want to fuzz? My first and very practical reason is that you can earn money if you find security issues with fuzzing in widespread applications like, for example, web browsers. And the quite similar reason is the money that you can spare if you find these issues earlier in your own application than hackers or other bug hunters do. Of course, I have more traditional motivations too. For example, that fuzzers can find real issues, meaning that they usually find crashes, memory corruptions, assertion failures, and so on, because they can only catch such kind of failures. What's more, their issues are often, or almost every case is reproducible, because we are completely aware of the circumstances and about the test case that triggered the failure first. And last, you can generate large amount of test cases just with a little initial effort while you write your test generator. Okay, so let's start it. What are the mandatory components if you would like to have a fuzzer framework? Well, first of all, you will need a target application that you want to torture and that you would like to find issues in. This is also often referred as software under testing or shoot in short. Next, you will need, of course, a test generator that can provide large amount of test cases that will be fed to the target application. But all of these worth nothing if you cannot transfer these test cases to the target application. This can be quite simple if your application is a command line tool that accepts input also from command line, but it can be more tricky if your application waits for input, for example, from the network or, for example, by user interaction. And this is why you need a transfer mechanism that can do this for you. And last, all of these worth nothing again if you cannot capture or save the reproduction cases that made your application fail. Okay, if you have these 4 components, then you can say that you have a fuzzer framework, but it's still far from being convenient or effective, and we will see why. Speaking of fuzzing, you will generate large amount of test cases, and hopefully many of them will fail, but also probably many of them will reveal duplicate issues, and these issues must be unified. This unification can be done, of course, manually, but it results in a long triage phase, which is not so convenient, but you can do it automatically too. Okay, so supposing that your goal is to report issue, and you would like to be popular among the developers who will fix your failure, then you should reduce your test case, because sending megabytes of randomly generated sources is not so nice. So this step can be either done by manually, iteratively removing chunks from the input, and if you are lucky, after a few hours, you will have a nice and small test case. But you shouldn't waste your time, because this can be automatically too. Okay, so you have a nice reduced test case, and you would like to report it, but creating a bug report only with a test case is not so nice. So you need to provide additional information describing the circumstances of your failure, like platform information, the version of the target application, some GDB information, for example, etc. And this information also can gathered automatically. And issue reporting, again, can be done manually, logging into the tracker, or you can use public tracker APIs and can perform the report automatically again. Okay, let's suppose that you have a target and you would like to fuzz it continuously for days, for weeks, or for years. Then you probably will face the problem that you should update your target to make sure that you always test the bleeding edge version of the application. So your framework is nice if provides some kind of scheduling for should update. Okay, let's go even further and suppose that you have multiple targets, you have multiple test generators. You would like to update your target regularly, you would like to perform different fuzz jobs, and you even would like to reduce the test cases automatically. Then you will need a scheduler in your framework that can do this instead of you. And last, the icing on the cake, if you have a nice user-friendly and interactive UI that can give you full control over the running jobs, can give you information about the find bugs, can you report the find bugs, and you have some overview about the effectiveness of the various test generators. And here where we get to Fuzzinator, because it incorporates all the features mentioned earlier. So let's see what Fuzzinator is. Fuzzinator is basically a Python-based general fuzzer framework, which has extra support for browsers. But this support is not something hardwired thing. It's instead a set of plugins provided by the framework that you can load dynamically if you need them. If I would like to speak about Fuzzinator in short, then you can imagine it as a building toy and building blocks, and an initial set of building blocks covering the most general issues are provided by the framework itself, and which basic blocks you can use as they are, or you can customize it, or you can write or your own building blocks if you have special needs. And the good news is that you not necessarily need to dirt your hand with coding, but you can easily set up your framework by writing a simple config file. Being a bit more technical, let's see the basic architecture of Fuzzinator. The image shows only the very core part of Fuzzinator to help understanding. And as you can see, the heart and the initial point of Fuzzinator is controller, which is responsible for scheduling the three types of jobs: the update, the fuzz, and reduce jobs. The green line on this image represents the API boundary of Fuzzinator, and everything below this are part of the core framework, and everything above the line are customizable by you, either with using the predefined building blocks or using your own blocks. When you start Fuzzinator, then it will check whether any of your targets are outdated and update it if this is the case. After the updates, it starts a regular fuzz job, which hunts for new issues, and the new issue has found, then it will be saved to a database, and if the current fuzz job has ended, then controller will pass these find issues to the reduce job, which will perform the test case reduction. So, as I said, basic blocks are here, and these blocks can be used from the Fuzzinator framework, or you can use your own. The only thing that you have to fit into the minimal expected interface. For example, the fuzzer block needs to provide one or more test cases as an output. These test cases will be fed to the should call block, which is responsible for running one target application and capturing the issues, if it were any. These issues are described by an issue dictionary, where every field describes one property of the failure. And the last part is the reducer, which we also have two options provided to you. Or you can use your own version. This reducer will work iteratively, and in every iteration it will remove parts from the input, and in every iteration it will test this chunked input and will see if it still reproduces the issue or not. For this check, we use again the should call basic block or building block to ensure the same environment that we had during fuzzing. Furthermore, it also makes possible to capture those bugs that were revealed by the test case reducer, and these new revealed bugs will also be saved and scheduled for further processing. Okay, so we have now some kind of imagination how the architecture of Fuzzinator looks like. Now we see those building blocks that are provided by the framework and that you can use out of the box. The first such block is the should call block, which is responsible for starting the application, loading the test case, and capturing the issues. And supposing that you have an application that you can run from command line, that accepts test case from command line, and that exits on failure, then you can use the built-in subprocess call solution. But if your application doesn't exit on failure, but present an error message on one of its streams, then stream monitor subprocess call is for you, because it will monitor the output of the application and will interrupt it if a nasty pattern has found. Or if you have an application that reads from std, a standard input, then we have solution for this too, and this is std subprocess call. The next and the last option that we provide for you is test runner subprocess call, which is a browser-specific runner which wraps WebKit test runner, if anybody knows it. It's the WebKit's testing engine, and it also has special needs to execute. Beyond these options, you have the possibility to write your own runner. The only expectation is being a Python callable and put it to your Python path. Okay, now we can execute our target, but we can tweak it even more with using decorators. Decorators are here instance of Python decorators, meaning that it can wrap a function, it can capture its input, it can capture its output, and optionally can modify it. And this will perfectly fit to our needs. For example, we can use it for filter out or discard issues that we are not interested in. For this, we provide two solutions. We can filter by exit codes, or we can filter by regexes. And the other option of decorators is extending the knowledge about the issues we found. This means that we can extend the result issue object with extra fields that can contain platform information, version information, GDB information, or anything you like. And here you can write your own extender again. Speaking of fuzzing, we have some predefined solution for the most general fuzzing issues or fuzzing steps. For example, we can generate random string, we can iterate over a directory and get test cases from them one by one and feed it to the target application. Or if you have an external test generator, then you can use subprocess runner, which will execute your generator and will feed the generated test cases one by one again back to the target application. Or if you favor AFL, then we have a wrapper around AFL too. This can capture the issues found by AFL and can triage the same way as every other issues and can gather information for them. And of course, you can hear your own callable again. And here we have a single decorator, which is a browser-specific thing again. It's called Tornado Decorator, and it's used to start a web server and push the generated test cases through HTTP, which is quite useful if you have a browser as a target. And our last building blocks are reusers. We have two options for you. Pizzeria and Pizzerani, both of them is available from GitHub and released a few months ago. Both tools are based on the traditional data debugging algorithm, but they are extended and both of them can run in multiprocess mode, speeding up the original algorithm very much. And the difference between Pizzeria and Pizzerani is that Pizzeria works character on line base, which means a dummy reducer, and Pizzerani can make use of syntax knowledge of the input format and can generate or can reduce the test case in much less steps. Okay, so we have the main building blocks and we have some kind of imagination about the architecture. Now let's see how can you configure your own Fuzzinator instance. As I said, you don't necessarily need to write code, but you can write instead a regular iniconfig file with two mandatory sections, with the shoot section and fuzz section. As the name says, shoot section will describe how your target application will be run, how often should it be updated, how can you reuse the test cases for this shoot, etc. While fuzz section will bond the target application and test generators together. And last, you can have a global Fuzzinator section, which describes global information about it. For example, you can give the database URI of the database that you would like to save your issues into. And the further sections will be describes the previously mentioned building blocks parameters, but we will see an example soon. Okay, but we would continue with the real example. I would like to show you an example test generator, as I promised at the beginning. It's named generator ret, which is basically a simple idea, fuzzer, It can process large amount of existing HTML test cases in a preliminary step. It collects information from them, and using this information, it will generate test cases later. In the sense of the previous presentation, it's a dumb fuzzer because it's not guided by coverage or anything else. But in contrary, it is aware of the syntax of websites, HTML, CSS, etc. And it gathered semantic information from the test cases, so it will generate valid test cases. And it actually works because it reported issues just yesterday from WebKit. So if you try it, I'm sure you will find issues. The source code is available from GitHub. You can check it, try it, modify it, anything you would like. And now let's see how can you bind it to Fuzzinator. You can see a minimal ini file on the projector. This snippet describes the should call block in config file sense. Every should call block has to start with the should prefix and continues with the name of the target application. It has to contain one call field, which points to a Python callable. In this case, this callable is the subprocess call, what I mentioned earlier, and which is part of the Fuzzinator framework. This subprocess call will execute WebKit, parameterized as you can see in the next section. The section name is built from the original should section name plus the call postfix. Subprocess call in this case will receive a current working directory value and a command value, which command value describes how WebKit or how mini browser can be started. As you can see, there is a test keyword here, which will be replaced in every iteration by the framework itself. Okay, but we would like to extend our subprocess call with issue detection, and in this case it will be simple. We will only grab for a few error pattern. Like in this case, we will look for assertion failures. Our next decorator will be extend our issue object with an extra field, and this extra field will be called version, and the value of version will be filled with this command result, which gives a Git version information. Our last decorator is platform info decorator, which is also a built-in option for us, and it will fill the platform field with the platform information gathered by Python. And last, we define a reducer for WebKit, and in this case, this is the pizzeria reducer, as I mentioned. And because we can use pizzeria with default parameters, we don't need an extra section for this. Okay, here we have a should section. Now let's see how a fuzz section looks like. As I mentioned, the fuzz section is responsible for binding the should application with the test generator itself. And the test generator here will be generator, that's what we saw in the previous slide. So fuzz section must start with the fuzz prefix and must contain at least one should and one fuzzer field. Should field refers to the section describing our should, while fuzzer is a reference to a Python callable, which is a subprocess runner now, and it's very similar to subprocess call. It has similar parameters than subprocess call. You can see how generator can execute it. You can show an output directory and the number of test cases you would like to get. And last, here is an example, because we are speaking of browsers. How can you apply Tornado Decorator on the subprocess runner. And as a result, if you start this fuzz section, the mini browser will get test cases. Will get the test cases generated by Renata via HTTP instead of loading it from file. Okay, and a screenshot about the text-based user interface of Fuzzinator. On the left panel, you can see the currently running jobs. On the right top panel, you can see the issues found by Fuzzinator or any of the test generator. The colors codes the status of the bugs. Yellow means that it's reduced already but not reported. Gray means that it's reported already, and the white color means that they are newly found bugs. On the bottom panel right, you can see a statistic about your test generator. You can see how many test cases were executed, how many of them crashed, and how many of the crashes were unique. Okay, and last, a screenshot about the report window of Bugzilla. All the information here were generated automatically, and also the fields were generated automatically based on the Bugzilla API. The reporter makes you possible to find possible duplicate reports, and you can choose it as duplicate, and then you set it into your database too. Or if you consider this issue still unique and still worth to report, then with clicking on the report box, you can send the report itself. And basically, this is all from me. If you have any questions, then you can say it now, or you can reach me out via Twitter or email or the outdoor box. Okay, yes?